Hi ladies and gentlemen, let me welcome you to the 19th session of ECT 204 Signals and Systems. Today we enter into the second module. Here we will see the Fourier method of signal decomposition. Today's speech is organized into your learning outcome, then the landmark work of Joseph Fourier, and then we will see what Fourier series and Fourier transform are. Then first we focus on Fourier series. First we will compute the Fourier series of a square signal, and we will demonstrate it with Python, and then we see the line spectrum of such a signal and the summary of understanding. So the learning outcomes in this session are: first you will appreciate the history of Fourier series and its applications in engineering. Here we will digress a little upon Joseph Fourier and the history of Fourier series. Then you will appreciate the critique by Lagrange, the great French mathematician, and its significance in signal analysis. Then you will understand the application regimes of Fourier series and transform. Where do you use Fourier series and where do you apply Fourier transform? Then you will learn to compute the Fourier series of a rectangular periodic signal and understand that it is a sum of odd harmonics. Then you will appreciate the demo with a different number of harmonics. During his lifetime, young Baptist Joseph Fourier was considered as a serious Egyptologist and as a government official rather than as a mathematical physicist. During his time, his works were mostly in expedition to Egypt and interpretation of hieroglyphics, etc. So at that time he was a government official, as a serious government official, and he was a great Egyptologist. He was not considered as a great mathematician at that time. Then he published an essay on the propagation of heat in solid bodies. Then Fourier wrote the groundbreaking work, The Analytical Theory of Heat. So in that he proposed this proposed the representation of a periodic signal as a sum of sinusoids and cosinusoids. And he published it to an institute in mathematics, but the then great French mathematician Lagrange opposed its publication on the ground that Fourier method fails when there are discontinuities. So it was a valid critique, and it took about 15 years and Lagrange's death before Fourier could publish the second work. But by the time Fourier was very busy with expedition with Napoleon to Egypt and all that. So, but after publication, this the Fourier's theory paved way to many developments in science and engineering. Now, Fourier analysis decomposes a function or signal into orthogonal components. Namely, here it is sine and cosine components. Fourier series is used to decompose periodic power signals, and Fourier transform is used to decompose non-periodic energy signals. That is, if you want to orthogonalize a periodic power signal, say a sinusoid or cosinusoid or a repetitive waveform or a repetitive signal, you use Fourier series for decomposition. And if you are working with non-periodic energy signals, we use a Fourier transform. So you have to understand the application regimes of Fourier series and Fourier transform. First we focus on the Fourier series. Suppose I have a periodic continuous time signal, that is xt is equal to xt plus or minus t, or xt equal to xt plus or minus k times t, where k is an integer, that satisfies the Dirichlet condition. So what are these Dirichlet conditions? First condition is the function xt has a finite number of discontinuities in each period. That is, xt should be, we should know the number of discontinuities in each period. Then the function xt has a finite number of maxima and minima in each period. Then it should be, this function should be absolutely integrable in one period. That is, integral from 0 to t mod xt dt should be finite. Then if these three conditions are met, I can put xt as a sum like this, that is k from minus infinity to infinity, ck e raised to j 2 pi kt by t, where k is an integer. So every k, each k contributes to a harmonic. And the coefficient ck is computed as ck is 1 by t minus t by 2 to t by 2 integral xt raised to minus j 2 pi kt dt. Now you have to see that I use a kernel e raised to j 2 pi kt in the expansion, kt by t in the expansion. So I should be using the conjugate kernel in finding this ck. So these are the two principal equations, xt equal to km minus infinity to infinity ck e raised to j 2 pi kt by t, where 1 by t is your period or 1 by t is the frequency of your signal or the fundamental frequency of signal. Every k contributes to a harmonic. And ck is 1 by t integral minus t by 2 to t by 2 xt e raised to minus j 2 pi kt by t dt. Note that I use a conjugate kernel here. Now let us expand this slightly. That is, if I look into the equation xt k from minus infinity to infinity ck e raised to j 2 pi kt by t, but e raised to j theta is cos theta plus j sin theta. Now xt is k from minus infinity to infinity ck e raised to j 2 pi kt by t. Now this e raised to j theta is cos theta plus j sin theta. So if I expand this k from minus infinity to infinity, it becomes ck cos 2 pi kt by t plus j sigma k from minus infinity to infinity ck sin 2 pi kt by t. So effectively I have written this into cosines and sinusoids. Now if I expand this, I have a central term called C0. When k equal to 0, this e raised to j 0 becomes a 1 and C0 alone is there, that is a middle term C0. Okay. And I have when k is minus 1, I have a cos 2 pi into minus 1t by t c minus 1, and I have a sine term here c1 or rather I will start from here. I will put the cosines together, like I have a c minus 2 cos minus 2 pi into 2t by t plus c2 cos 2 pi into 2t by t. These are the second harmonic, okay, c minus 2 and c2 cosine terms together. And I have c minus 1 cos 2 pi into minus 1t by t plus c1 into cos 2 pi into 1t by t. Then the middle term, that is a c0, then I combine the signs together, that is plus j into c minus 2 sin 2 pi into minus 2t by t plus c2 into sin 2 pi 2t by t, and c minus 1 sin 2 pi into minus 1t by t plus c1 sin 2 pi into 1t by t. So if I combine them together, what happens is xt is c0, that is a DC time, that is when k equal to 0, that is a DC time. K equal to 0 means it is a DC time, that is c0 plus c minus 1 plus c1 into cos 2 pi into 1t by t plus c minus 2 plus c2 into cos 2 pi 2t by t plus etc. plus the remaining sine times j into c1 minus c minus 1, because here this sine minus theta is a minus sine theta. So c minus 2 sine becomes a negative and c minus 1 sine becomes a negative. So here I have a j into c1 minus c minus 1 sine 2 pi into 1t by t plus j into c2 plus c2 minus c minus 2. I am sorry, here is a mistake, I will correct that. Here I have this is c0, that is my DC time, plus c minus 1 plus c1 cos 2 pi into 1t by t plus c minus 2 plus c2 cos 2 pi into 2t by t plus etc. These are the cosine times. Then there are the sine terms, that is j into c1 minus c minus 1 sin 2 pi into 1t by t. That is j c1 minus c minus 1 sin 2 pi 1t by t plus j into c2 minus c minus 2 sin 2 pi 2t by t, that is second harmonic. So I can combine them together with another set of constants. I replace the C0 by A0 and C minus 1 plus C1 by A1 and C minus 2 plus C2 by A2, so that likewise I replace J into C1 minus C minus 1 by, say, B1 and J into C2 minus C minus 2 by B2, etc. So that this equation becomes, xt becomes A0 plus A1, that is C minus 1 plus C1 cos 2 pi into 1 t by t, plus A2 that is C2 plus C minus 2 cos 2 pi 2 t by t plus etc. plus B1 into sine 2 pi into 1 t by t plus B2 sine 2 pi 2 t by t plus etc. This I can generalize as A0 plus k equal to 1 to infinity ak cos 2 pi kt by t plus k equal to 1 to infinity bk sine 2 pi kt by t. Now, where are these? Which are these ak and bk? Ak is ck plus c minus k, and bk is j into ck minus c minus k. Now, what are these ck values? Earlier I have computed ck here. This is the integral for ck. So, if I put it here, I have ak is ck plus c minus k. So, it becomes 1 by t minus t by 2 to t by 2 xt raised to minus j 2 pi kt by t dt plus 1 by t into minus t by 2 to t by 2 integral xt raised to plus j 2 pi kt by 2, because it is c minus k. Now, what is this e raised to j theta plus e raised to minus j theta? That is a cos theta. So, 2 cos theta. So, it becomes a 2 by t integral from minus t by 2 to t by 2 xt cos 2 pi kt by t dt. And when it comes to bk, what is bk is j into ck minus c minus k. That becomes a j by t integral from minus t by 2 to t by 2 xt raised to minus j 2 pi kt by t dt minus j by t into minus t by 2 to t by 2 xt raised to plus j 2 pi kt by t, because k is a c, it is a c minus k value here. So, what is this e raised to j theta minus e raised to minus j theta? That is a 2j sin theta. But it's a e raised to minus j theta, e raised to minus j theta minus e raised to j theta. So, it's a negative sign also. It becomes 2j into j by t minus t by 2 to t by t xt sine 2 pi kt by t dt. Okay. This j square is minus 1. So, this integral defaults to 2 by t integral from minus t by 2 to t by 2 xt sine 2 pi kt by t dt. So, this is another, this is an alternate way of representing the Fourier series. Either I can say it is a ck e raised to j 2 pi kt by t summation with ck this, or I can say in terms of an and bn. Now, let us see one simple example. Let us compute the Fourier series for the periodic signal here. This is a square signal, say this has a period of t. From here to here it is a t, one period is a t, its amplitude is a, it is bipolar, amplitudes a and minus a. Now, let us compute the Fourier series for this signal. Now, let us compute this ck for this. Ck is 1 by t over 1 period xt e raised to minus j 2 pi kt by t dt. So, it is 1 by t from 0 to t a e raised to minus j 2 pi kt by t dt. Okay. So, where is this period? It is from, we have taken from minus t by 4 to t by 4 and t by 4 to 3t by 4. Let us look at this period. Say this is a minus t by 4. Okay, this is a minus t by 2, half of that is minus t by 4 to plus t by 4. Okay, and t by 4 to 3t by 4. This point is t by 2 and this is another half of that. So, this point is a 3t by 4. So, my integral changes from 1 by t minus t by 4 to t by 4 a e raised to j 2 pi minus 2 pi kt by t dt plus t by 4 to 3t by 4, the amplitude is minus a. So, minus a e raised to minus j 2 pi kt by t dt. So, for the first one, this is a, you can see that a comes out. There is a common term j 2 pi k by t, okay, So then I have e raised to minus j 2 pi t by t. So this becomes the upper limit, it becomes e raised to minus j 2 pi by t into kt by 4 minus lower limit is it's a plus sign, e raised to j 2 pi t by t into kt t by 4. Then I have this term, the second one, they come as minus e raised to minus j 2 pi t by t into k 3t by 4 plus it's a positive sign plus e raised to minus j 2 pi into k into t by 4. It has overlapped here. Now it becomes a by t, this t will be cancelled, it becomes aj by 2 pi k into this becomes e raised to minus j pi k by 2 minus e raised to plus j pi k by 2 minus e raised to minus j 3 pi k by 2, and this is e raised to minus j pi k by 2. So this becomes, I have 2 of this e raised to j pi k by 2, so this becomes 2 e raised to minus j pi k by 2 minus e raised to j pi k by 2 minus e raised to minus j 3 pi k by 2, all multiplied by aj by 2 pi k. So that it becomes, again this e raised to minus 3 pi by 2 becomes e raised to plus j pi by 2. E raised to minus j pi by 2 is nothing but e raised to plus j pi by 2. So it becomes 2 e raised to minus j pi k by 2 minus 2 e raised to j pi k by 2. So this 2 is cancelled, it becomes a by j pi k into e raised to j pi k by 2 minus e raised to minus j pi k by 2. Okay. So I have removed the minus sign by placing this j at the denominator. So this 2j sine pi k by 2, so that j is cancelled, it becomes 2a by pi k sine pi k by 2. Okay. And now here, if you put k equal to 0 here, there is a division, there is a wrong division by sine 0 by 0. That means it is wise I compute C0 separately. So if I want to compute C0 separately, how do I do? This is my Ck, equation for Ck. In this I put k equal to 0, so that it becomes 1 by t 0 to t, xt dt will give you my C0, which is nothing but the average value of the signal. So expression for C0 is 1 by t 0 to t xt dt. Now you can see that this is the area under the curve xt for one period. Now the signal has equal positive and negative excursion. So over one period that average value will be 0, because it has equal positive excursion A and negative excursion minus A. So the average value of this signal is 0. So C0 is a 0. And I can compute the C1, C minus 1, etc. C1 is 2a by pi. Here if you go here, when k equal to 1, sine pi by 2 is a 1. So it is a 2a by pi k. Okay, and when k equal to minus 1, this becomes a minus 1 by minus 1. So again 2a by pi. And C2 and C1 and C minus 1 are equal, that is 2a by pi. And C2, if you put to k equal to 2, it becomes a sine pi, so that's a 0. So C2 and C minus 2 are zeros. And if you say C3, C3 will be 2a by 3 pi sine 3 pi by 2. That is nothing but minus 2a by 3 pi, and C minus 3 is minus 2a by 3 pi. C4, if you go here, if you put k equal to 4, it becomes sine 2 pi, that's a 0. Now C4 is a 0, C minus 4 is a 0. C5 will be a 2a by 5 pi, and C minus 5 is a 2a by 5 pi. C6 is a 0. Now here you can observe that all even harmonics are absent, because C2, C4, C6, they are all zeros. Only the odd harmonics are present in the signal. So this is how I can compute the C values. Now since Cn is C minus n and Bn equal to 0, A1 will be double of this, A1 will be double of this 4a by pi. So A1 is 4a by pi, A2 is 0, A3 is minus 4a by 3 pi. We just double the value of C1, so Ck, so that will be Ak. But Bk, all Bk values are 0. So A5 is 4a by 5 pi, and A7 is minus 4a by 7 pi, etc. A2, A4, A6 are all zeros. Even harmonics are all zeros. Now, what is the value of my Fourier series? I have only cosine components. Not only that I have only cosine components, I have only odd harmonics. So, xt is 4a by pi into cos 2 pi t by t minus 4a by 3 pi into cos 2 pi into 3t by t plus 4a by 5 pi into cos 5 pi 2 pi into 5t by t plus etc. Minus 7 etc. So, you can see that every other term is a negative term. Okay. It means that the square signal is a sum of odd harmonics. Being an even signal, it contains only cosine components and not sine components. Now, here in this equation, if you put t equal to 0, I will be looking at the value at t equal to 0. The function value is a. You can go back and see if I put the value t equal to 0, the function value is a. Now, if I put t equal to 0 in this equation, xt will be a, so that it will be this a will be cancelled. So, if I move this pi and 4 to the left side, it will be pi by 4 equal to 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 etc. Or you can use this Fourier series, an approximation for pi. Pi will be 4 times 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 etc. That's an infinite series expansion for pi. It's a digression, but it's an interesting observation. So you can observe the demo with pi. Then I will show how this how I can realize this with pi. Then and what will happen if I add more harmonics into that, and we will see what the objection by Lagrange was initially and how it affects the signal theory. So we will go back to that code. Now, I have here the NumPy is included, the matplotlib is included for plotting. Now, I have a lin space, np.lin space from 0 to 4. I have taken 5000 values, a vector of 5000 values is taken, and I have created a square wave here. Okay. Now, let us take only first 2 values only. Say, let us take the first 2 values of the Fourier series and see how it looks like. And now, the frequency of the square signal initially it is put as a 0, and then for I in range 0, n or range n, what I do is I compute the odd harmonics 2i plus 1, and frequency is added to the frequency term is added. That is an np sine n pi x by n. This is my earlier coefficient. So then it is multiplied by 4 by pi. That is a time. Here I assume that the amplitude is a unity. Now then the square wave is plotted, and on the same GUI I plot both the square signal as well as the Fourier approximation, that is FSQ, that is a Fourier approximation, Fourier series for the signal with n equal to 2. Now let us see what happens when I run this code. You can see that the blue line, that is my square wave, ideal one, and the red curve, that is a Fourier series expansion with n equal to 2, that is just the first 2 harmonics, that is f equal to 1 by t and f equal to 3 by t. So you can see some 2 ripples happening because I have taken 2 terms of the Fourier series. Now you can see that at the edges you can see some rippling here. I will add more terms, and we will add more terms and check. Say I will make it f5. I take the first 5 terms. Let us see what happens. Now you can see that there are 5 ripples in here. You can see 5 ripples. You can see that at the edges, at the center during the DC part they more or less follow, but you can see that when there is a discontinuity, you can see that these ripples occur. This was the original opposition by Lagrange. It was later known as Gibbs phenomenon. So let us add more time. But you can see that it comes the Fourier series comes closer to the square wave, but still then you can see some ripples there. We will make 1000 or 1000 times. Now here you can see that the Fourier series is far closer to your original square wave, but even with 1000 times you can see that at the edges, I will zoom at the edges. At the edges, you can see that still there are some oscillation happening at the edges. This is called the Gibbs phenomenon. This was the original critique by Lagrange. The critique by Lagrange was later in signal theory. It is called the Gibbs phenomenon. So this is how the Fourier series behaves. You may copy this code and you can appreciate this at home. Now, this is how the approximation happens. So, if you look into Fourier series, the big disadvantage of the Fourier series, there are many advantages, but when it comes to discontinuities, the disadvantage of the Fourier series is its convergence issue, especially when there are discontinuities. For converging to the actual value, you need a large number of times, you need a large number of harmonics. So, now let us plot this ck square, mod ck square, that is the line spectrum of the signal. So, we will take each ck value and plot it. We will get the line spectrum of that. I have another code for that. So, here I assume that A is 1. So, I keep an array blank, so that to which I can add this spectral value mod ck square. Oh, here I have put mod ck square. This is if k equal to 0, s value equal to 0, the even harmonic is 0. Otherwise, the odd harmonic is 2a by pi k sin pi k by 2. I take the absolute value and square it, and I add these values to my initially blank array. And then I make a stem plot of this mod ck square against the index. So, then I try to compute the total power in the signal, that will be sigma mod ck square. So, that is a p value. We will run this code. Oh, there's a syntax error. Now, you can see that this is mod ck square plotted against k. This is a value k equal to 0, that is a DC value, there cannot be any DC value. This is a value for k equal to 1, this is a value for k equal to minus 1, that is, this is c minus 1 square, and this is c1 square, and this is c minus 1 square. You can see that that is very prominent, that is around 40% of the total signal power is carried by the first harmonic, that is 1 by t, that is a thing. And if you go to k equal to 2, the value is 0, because there cannot be any power in that second harmonic. The second harmonic is 0. And if you go to the third harmonic here, you can see that it is 0.05. While 40% of the power is in the first harmonic, only 5% of the power is in the second harmonic. Okay, this is the third harmonic. This is the fourth harmonic is a 0. Fifth harmonic, you can see it is very small. It's about 0.01 something. Okay, only 1% of the power is in the fifth harmonic. So this is how the power is distributed in the different odd harmonics of the Fourier series. And if you look at sigma ck square, that is a power in the signal, that is, it's a unit approximately unity, because I have taken only 100 values. You can see that I have taken only 100 values, minus 10 to 10. So that is why it shows, instead of unity, it's showing 95.96% of the power. But you can see that even with the first 20 components, I have taken 20 components. So if you look at the if you take the mode value only, if you take the 10 components, you can see that 95.96% of the energy falls in the first 10 components. Okay. So this is how you can appreciate the Fourier series of a square signal. Now, we are coming to the end of the video, summary of understanding. So, in this video, you appreciate the history of Fourier series and its applications in engineering. Then you appreciated the critique by Lagrange and its significance in signal analysis. The critique by Lagrange was that you need a large number of times to represent the signal if there are discontinuities. So, that was later known as Gibbs phenomenon in signal analysis. Then you understood the application regimes of Fourier series and Fourier transform. Where do you use a Fourier series? If you want to decompose a periodic power signal, you use a Fourier series. If you want to decompose a non-periodic energy signal, you use a Fourier transform. Then you learn to compute the Fourier series of a rectangular periodic signal and understood that it is a sum of odd harmonics. Then you saw the relation with pi, how to compute, how to approximate pi with the Fourier series of a rectangular signal. Then you appreciated the demo with Python demo with a different number of harmonics. You understood the line spectrum of the Fourier series of the rectangular signal. And that is the end of this presentation. I thank you all.